What if everything in the universe was actually a bit to the right of where it is now? Or if this orbiting planet was actually half a rotation ahead? What changes? More importantly, what stays the same? These seem like fun but useless thought experiments until Noether discovered what I think is the most profound and far-reaching idea in physics. Knowing what happens to a system under these imaginary transformations gives us insight into the system's real behavior. The usual summary is symmetries imply conservation laws. In this video, I'll explain what that means. We'll start with symmetry. Normally we use the word symmetry to mean that if we took the mirror image along some line, a symmetric object looks the same. Mirror symmetries like these are pretty, but we can make the word symmetry mean so much more. For example, rotational symmetry, when you can rotate an object by a certain amount and it looks just the same as before. Or another example is translational symmetry. In fact, mathematicians took the idea of symmetry and generalized it completely. A symmetry is anything where you have some sort of object and apply some sort of transformation to it, and you can't tell the difference, in some sense. This might seem like they've taken a good descriptive word and then generalized it until it's meaningless, but actually this idea is very useful. These abstract symmetries are a constantly reoccurring theme in mathematics. In fact, the study of symmetry helped motivate one of the most important fields of modern mathematics, called abstract algebra. Noether was an expert in symmetry, having developed foundational concepts in abstract algebra. It was during a small pause from her extremely influential mathematical career that she thought about physics. She wondered if she could apply the idea of symmetry to the world, and that's what led her to her beautiful theorem. This is the symmetry that she considered. The object is some system, a part of the universe. It could be a thing someone's throwing, or a particle in a void, or maybe some binary stars, or, if you want, the whole universe. Then you transform it. For example, you could rotate it by some angle lambda, or shift it up or down by lambda, or stretch all the distances by lambda. Now we're interested in if this system is the same in some sense. Noether decided the interesting thing to check is if the total energy of the objects would be the same. So we say that a system has a symmetry under a transformation if the total energy of the objects didn't change after that transformation. For example, if I had a particle all by itself and then compared it to a shifted version, clearly the energies are the same, so this system is translationally symmetric. On the other hand, say there was some big planet nearby. A particle that is closer has got more gravitational potential energy, and so this isn't translationally symmetric. Or consider this object orbiting in a circle and compare it to a rotated version. Both objects are an equal distance from the planet, and so both ways they have the same gravitational potential energy, and so this system is rotationally symmetric. So that's the symmetry part of Noether's theorem. Now let's look at conservations. If you've ever studied physics, for example at school, you'll know how important these things called conservation laws are. It means that if you have a bunch of things and you counted up their total momentum, let's say, then you let them go for any amount of time and counted the momentum again, it would be the same number. Technically, you can do physics without ever needing to use these conservation laws, but sometimes you'll be given some insane problem that looks like you shouldn't be able to solve, at least not very easily, but if you invoke the magical conservation laws, your answer just falls out. Conservation laws aren't just useful in classical physics either, they help out in quantum mechanics and really all of modern physics. I used to not like using conservation laws because they can make it seem too easy. As in, I'd get the solution with so little work that it really felt like magic, and so I didn't feel like I understood why it worked. After all, I didn't understand why energy is conserved or why momentum is conserved, and so if I used one of those to solve a problem, then clearly I didn't understand the solution. Noether's theorem is powerful because it tries to explain where conservations come from. So let me go back to an example. I said that momentum is conserved, but this is kind of not always true. If I chose my system to be a ball rolling on the ground, we all know that eventually it stops. Or if I drop something, it gets faster and faster. Sure, if you take everything as your system, then momentum is always conserved. But how can I know whether a particular system's momentum won't change? Noether's theorem gives us a simple way to know, regardless of whether the system is one particle or the whole universe. She proved that you only get conservations if the system had the right symmetries. Again, let's look at examples. If you have translational symmetry, the theorem says that you have conservation of momentum. We know that a particle that's on its own has this symmetry, and so its momentum is conserved. And we know that's true. It will continue on at the same speed in the same direction forever. If we instead had a bunch of particles by themselves as our system, this system is also translationally symmetric. If they were all over there instead, that doesn't change their energy. So again, Noether tells us that we have conservation of their total momentum, which wouldn't be that obvious otherwise. In fact, if we considered a shifted over version of the entire universe, no one would be able to tell the difference, and so there's clearly no difference in the energy. Hence, the momentum of the whole universe is conserved. When isn't momentum conserved for a system? What about this object that gains speed as it falls? Noether's theorem says that this system can't have translational symmetry, so let's check. What if this object was nearer to the ground? It would have less gravitational potential energy. Good, so it isn't symmetric. What about rotational symmetry? Like we said, this object could have been rotated here and the energy wouldn't change, and so it has rotational symmetry about this axis. We also know it has angular momentum in this direction, and that it goes at the same speed the whole way around, and so its angular momentum is constant, in other words, conserved. And this is what Noether's theorem predicts, that if you have rotational symmetry about one axis, then the angular momentum in that direction is conserved. So one last example, and this one is a weird one. We've talked about translating in space and in angle, but what about translating in time? In other words, you have a system doing something at a particular moment, and then you compare it to the same system sometime later. If it has the same energy, then it is time translation symmetric. What does Noether say is conserved then? It's the energy. I know that's a bit circular here, but it's more important when we come to quantum mechanics, so I had to mention this one. Noether didn't just come up with these three examples. Instead, she gave us a mathematical way to turn any symmetry into a conservation, and vice versa. See, these conserved quantities are called the generators of these transforms, and you can calculate what the generator is for any transformation that you come up with. If I encountered some exotic system and noticed it was symmetric under some transformation, there is a mathematical way for me to calculate what's conserved. There's also a converse. Say I notice some mysterious new quantity is conserved in some system I'm interested in. Noether's theorem says that that conservation is from some symmetry, and the conserved quantity is the generator of that transformation, so I can calculate what that transformation was. That's very powerful, but the theorem is amazing because it is just as beautiful as it is useful. Symmetries appeal to us and seem natural. We think it makes sense that if the universe was shifted or rotated, that nothing should change. There's no difference between here and there. So showing that symmetry and conservation laws are equivalent shows that conservation laws must be just as natural. Homework this time is pretty gentle. I want you to let me know what you think of this idea. Have you heard of it before? Maybe you've heard about things like supersymmetry in physics. Try and find out how that's related to this. The version of Noether's theorem I talked about here is the one for classical physics, only a much less powerful version of the theorem than the one that she actually created. If you know some calculus and classical physics, maybe try and find one of the proofs for this theorem. And this is a fun activity. Try and come up with strange systems with strange symmetries, and see if you can figure out what's conserved.